So, welcome to Ancient Light. It only seems like 5 minutes I was last here talking to you, and this one, as you can see from the subtitle, is about imaging a quasar without a telescope. So let's start with a lockdown challenge. Some of you might have noticed that last year in 2020, life as we know it changed. That object gave rise to lots of objects similar to that when you were looking down trying to keep your 2 meters from everybody else. But I remembered Stephen Hawking's words. Remember to look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. So there's the challenge. We know that the universe is vast and ancient, and we know that large telescopes have imaged galaxies that are billions of light years distant. So the question is it possible to capture an image of one of these remote objects without a telescope? In other words, taking Stephen Hawking's idea, remember to look up, the question is, just how far can I look up? And spoiler alert, yes indeed, it is possible to image one of these without a telescope. So I found this article on a Quasar Survey, and a quasar is the nucleus of a galaxy that emits enough light to be seen at enormous distances. So it's a type of so-called active galactic nucleus. It's a black hole in which matter is falling in, whether that matter be gas or dust or other stars. Matter is falling in and a huge amount of energy is coming out. And that makes quasars bright enough to be seen at very great distances. So I looked at this particular survey and I found that there was one particular quasar. Of course, that's not an image of it, that's just an artist's impression, because all these quasars are so distant we can't really get a good handle on them. But I found one of the quasars in this particular survey was going to be visible high in the sky during the summer when I decided that this lockdown challenge ought to be taken on. So that might be what it looks like close up. A supermassive black hole which we can't see, a lot of matter falling in, getting very hot and producing a great deal of radiation. So returning to this particular paper, I found a particular candidate quasar, which was one that was in the constellation of Draco, high in the sky. This was somewhere around June, July. I started to think about this. So I wanted one that was very high in the UK sky during the summer. And this is the most distant quasar that I could find that would be visible from the UK. Goes under the glorious name of J161737, etc., etc., etc. Hasn't got a proper name. And these people who surveyed these various quasars looked at its spectrum, because the spectrum is essentially how you tell how far an object is away. And I don't expect you to be able to interpret this spectrum. It's looking at the intensity of light from the blue end of the spectrum to the red end of the spectrum. But we can take it from the people who did this work that they have recognized that that peak there, which occurs at a certain part of the spectrum, has been redshifted from a much smaller wavelength. So if you remember your Doppler shifts, if we're looking at a spectrum, then an object that's moving away from us gets all the wavelengths shifted to the red end of the spectrum. And if any object is moving towards us, all of the wavelengths get shifted towards the blue end of the spectrum. And so because they've identified this, we don't have to worry about how, but they've identified that as being part of the ultraviolet spectrum, and that should occur at 1200 angstroms, or 120 nanometers if you prefer. For some weird reason, astronomers tend to prefer using angstroms rather than nanometers. So we can quantify the redshift by saying how much has it shifted compared to where it would be if it wasn't moving relative to us. In other words, if a particular peak in the spectrum has moved from 1200 and has shifted by how much, the difference between 65 and 1200, so it's shifted by 5300, we divide one by the other to give us a quantification of the redshift. So the difference of those numbers divided by the first of those numbers tells us that this object has a redshift of about 4.3. And 4.3 is huge in terms of cosmology. A redshift of 0.1 is still quite a distance away. A redshift of 1 is a long distance away. A redshift of 4 means it's an enormous distance away, and we'll come to the distance shortly. So this is what I used. I took my camera. This is the camera that I tend to want to use if I'm taking wildlife photography. I'm not sure I've got a picture of a kingfisher quite like Terry, but this is the camera that I would use if I wanted to take some wildlife photography, a relatively modest telephoto lens. And I put that camera onto a star tracker. The white box here is a star tracker. This one is a commercial one that I bought from Ioptron. Other star trackers are available. They're either motorized or clockwork devices that will turn the camera in 1 day, strictly speaking in 23 hours 56 minutes, one sidereal day, so that if it's set up correctly and this polar scope on the left hand side is pointed at Polaris, then the camera will be rotated to follow the stars. So there's the camera I've used, a 300mm lens. F4 means that the diameter of the front element is 1/4 of 300, so it's approximately 75mm in diameter. This particular camera and lens, they are precisely the same combination that I use for wildlife photography. They're not customized in any way. The camera hasn't been modified for astrophotography. This is just a collection of technology which exists to take pictures in daylight, and I asked myself if that particular camera and lens is perfectly good to take pictures of zebras, which I love to do on safari. If it can take a picture of a zebra, can that same combination also catch a quasar on the other side of the observable universe? So, having identified where this particular quasar was in this catalogue that I looked up, I found that it was just next to this little star you see in that rectangle drawn into the constellation of Draco. You recognise there Ursa Minor on the right hand side and Polaris on the extreme right. That orange rectangle shows the field of view of a 300mm lens. And that dot in the middle, that's not the quasar. The quasar is far too faint to be visible in this star chart. That dot in the middle is a star called 80 Draco. And it just so happens the quasar is close by. So I could see that particular star through the viewfinder, and I lined up on that and focused on a nearby faint star of about magnitude 8 or so. I focused on that star and then figured that the quasar was not far away from that star, so it should be in the field of view. I didn't want to take a very long exposure. I took a series of short exposures for a number of different reasons. A, it's easier. B, if the tracking isn't absolutely perfect, there's no way I could guarantee that the camera continued to point in the right direction for all of 2 hours. So I took a series of shorter exposures and added them all together. It also gave the advantage that on that particular evening at the end of July, there wasn't a great deal of night time, so I had a couple of hours or so to catch a dark sky, but there were some clouds scudding by. So by taking a large number of short exposures rather than one long exposure, I simply went through the many images that I had and threw away all the ones that had clouds scudding by and left myself with all of the images that were looking at clear sky and added those all together to give me this particular result. And right at the centre there is our star 80 Draco, and the quasar, according to its coordinate, should be in the middle of that square. So I blew up that square until I could see what was going on, and right in the centre there, that's where the quasar ought to be. And I double checked by doing some plate solving, asking a particular web page, what particular right ascension and declination am I looking at according to these dots, and it told me the coordinate of the centre of that square was exactly where I expected to find the quasar. So yes, definitely captured it. Most of the light from the quasar is focused into, roughly speaking, 1 pixel. If we blow up the quasar, I've just exaggerated a little bit some of the fainter light, so you can see a few background stars as well, but I've just exaggerated just to show some of the additional pixels in the background, but most of the light has gone into that central pixel of the quasar. So the original camera produces a 20 megapixel image, but only 1 or maybe 1 plus the neighbouring pixels have caught the light from the quasar. Just as an aside, If we have a lens, and remember the front element of the lens is about 75 millimeters or so in diameter, what resolution could we expect, assuming that the lens doesn't have any significant aberrations? And given that I paid a few £100 for that lens, I should hope that there's no real aberration in the lens. Then the diffraction limit as to what you could possibly expect to get for resolution from a 300mm f4 lens, the diffraction limit is a little bit less than 2 arc seconds. And if we look at the spacing of the pixels in the camera and work out the angles for a 300mm lens, for the particular camera I've used, the pixels are about 3 arc seconds apart. And I would think the seeing on that particular night was perhaps a couple of arc seconds, so they're reasonably well matched together. Just to give an idea of scale, if we think about a distance of a few billion light years, how big would the Milky Way galaxy appear if it was at that distance? The Milky Way would appear to have a diameter of order 6 arc seconds. In other words, perhaps a couple of pixels or so. That just gives us an idea of scale. Also, I thought it was quite interesting when I took that particular crop just to see where the quasar was. I also compared the star positions with the positions of objects that I could find in a research telescope field, and realised that some of those are stars, but actually some of them are actually galaxies. Some of those stars that look a little bit elongated, it's no surprise to find that those were galaxies, little spiral or elliptical galaxies, and some of those objects are probably too faint for you to see, and they look just like stars. The only reason I know that they're galaxies is because I've compared them with professional plates of the same field. So if I've caught 10 galaxies in that small crop from the original image, assuming that's typical of the whole image, and there's no reason to assume otherwise, then there are probably about 7,000 galaxies in the original 2-hour exposure. And it's very sobering to realise that an exposure from your back garden can pick up 7,000 galaxies in one frame, when that's comparable to the number of galaxies that the Hubble Deep Field has picked up. Okay, I'm not claiming this is as good as the Hubble Deep Field, despite the title of this slide, but it's just interesting to note that you can pick up thousands of galaxies in one long exposure. So let's come back to the idea of the distance to this quasar. Some time ago, the centre of this galaxy produced some light which started its way towards the Earth. So you could say that was the distance then. There was a particular distance from the Earth to the quasar at the instant the light left the quasar. But of course it takes time for the light to travel towards the Earth. And as the light is on its way towards the Earth, the universe is continuing to expand, and so the galaxy, the quasar, is getting further away from us. And eventually the light arrives at Earth and enters my camera, and of course the galaxy is even further away. And you could call that, if you like, the distance now. How far away it is from the quasar to the Earth now that the light has arrived. But you can see the distance then, and the distance now, and the distance that the light has had to travel are 3 different measures, and they're all, if you like, the distance. There is no unique statement that says what is the distance from A to B when you're living in a universe which is continually expanding. So you have to make it clear. Are you talking about the distance when the light left, the distance when the light arrived, or the distance that the light has travelled? And that middle one is even more tricky, because if you think about, well, what is the distance that the light has travelled? Well, remember, as the light is travelling from the quasar to the Earth, space is continuing to expand. The light is travelling through space, but the space is not static in the sense that the universe is continuing to expand for the whole travel time from when it left the quasar to when it arrived at Earth. It's a bit of a tricky thing to get your head round, but it's a bit like saying, well, if the speed of light is always the speed of light, so a swimmer can swim through water at a particular speed, but what if the water is flowing? And what if the water is flowing such that you're getting dragged backwards? Because remember, space is expanding to the point where it's trying to drag the light backwards. So it's just like the swimmer trying to swim through a head tide where the tide is trying to pull him backwards whilst the swimmer is trying to go forwards. Another analogy which tends to work quite well is to think, well, what if an ant is moving along a rubber band? And whilst the ant is walking along the rubber band, what if you start stretching the rubber band? How far does the ant actually walk? Well, again, it's a tricky thing to work out because it depends on exactly how much you're stretching the rubber band, how quickly you're stretching the rubber band. In other words, how quickly the universe is expanding. So that is a rather tricky thing to work out, and it's not particularly intuitive because we don't tend to stop and think about what do things look like when they're travelling through a universe which is expanding. It's not a very intuitive question to ask ourselves. But if we did want to work out these distances, it can be done as long as we have some understanding of how the universe is expanding. And in particular, we have to understand how the universe was expanding when the light left, and how it's expanded throughout the entire journey of the light leaving a distant object and arriving here at Earth. And so I plotted those out in a little spreadsheet, and here are the distances. Red is the distance to the object now, for a given value of redshift. Remember, redshift is a measure of distance. It's not directly a measure of distance, but from the redshift we can calculate the distance. And red is the distance the object is now. Blue is the distance that the object was when the light left. And green is how far the light has travelled. So notice that if the redshift is quite small, when we look at the spectrum of a distant object, if the peaks don't seem to have moved much relative to where they would be in a static object, if the redshift was, let us say, 0.1 for instance, we would be down here and all of these distances would be about the same. In other words, if the object is relatively close to us, only 100 million light years or so away, then the universe doesn't have much time to expand in the length of time it takes the light to reach us. So the distance then and the distance now are virtually the same thing. But the further back in time we go, the larger the redshift, the further out we are looking, so the further back in time we are looking, the more universe has to expand, the more time it has to expand in the time it takes the light to arrive. So these three lines get further and further apart. And if we think about this particular quasar has a redshift of 4.3, which means we get these three numbers here. And let's just get rid of the lines because we don't need those anymore. If we're talking about this particular quasar, then we can say that, assuming we've got our understanding of the universe correct, then we can say that the quasar was approximately 5 billion light years away when the light was emitted by the quasar. The light has taken over 12 billion years to reach us. Remember that the universe is 13.8 billion years old, and we are talking about light that has been travelling for 12 billion years. The light has been travelling for 90% of the age of the universe. That is what I talk about when I'm saying it's a very remote object. It's so remote, it's taken 90% of the age of the universe for the light to actually arrive. And during those 12 billion years, the universe continued to expand, and so now the quasar is some 25 billion light years away. It was originally 5, and during the 12 billion year light travel time, it's gone from 5 billion light years to 25 billion light years. But if we think about those numbers, from 5 to 25 in a time period of 12 billion years, a quick back-of-the-envelope calculation tells us something very interesting is happening. During those 12 billion years that the light has been travelling, the quasar distance has increased from 5 to 25 billion light years. It's increased by more than 12 billion light years. Speed is distance over time. If it's gone from 5 to 25, it's now 20 billion light years further away now than it was when the light left 12 billion years ago. So its speed, on average, must be of order 1.6 times the speed of light. The quasar has been receding from us and still is faster than the speed of light. That's not a problem in the sense that light can travel through space at a speed no higher than the speed of light, i.e. c, 300,000 kilometers per second. But space is expanding and the quasar is along for the ride. It's not like the quasar is hurtling through space at this speed. It's that the universe is expanding and the quasar is being carried along by the expansion of space. And the light is trying to move through space, and it can only travel at the speed of light, but space itself is expanding at an ever-increasing rate. In fact, we can actually work out, again, given our understanding of how the universe is expanding, we can calculate that when the light left, some 1.5 billion years after the Big Bang, that particular quasar was receding from us at about 2.2 times the speed of light. And it was falling. Now, falling is not altogether unexpected. If the universe is expanding and gravity is pulling everything together, surely as the universe expands, gravity will slow down that expansion, and bit by bit the expansion of the universe will slow and slow and slow. At least that's what we thought was going on until a couple of decades ago it was realised that if you look at very distant supernova and work out the expansion of the universe now compared to the expansion of the universe in the past, it's actually starting to accelerate. So that velocity originally went down, but look what's been happening for the last 6 billion years or so. The recession speed of that quasar has actually been getting faster. It dipped as low as 1.5 times the speed of light, but now the quasar is at 1.7 times the speed of light and accelerating away from us. So it looks like the universe is expanding, and originally it started to slow down, but after a few billion years the expansion of the universe has started to accelerate. We've put a label on this. That doesn't tell us we understand what's going on, but the label we put on this is dark energy. Something is pushing the universe apart and making everything accelerate away from everything else. And that's why this curve doesn't simply come down, it comes down and then goes up again. So trying to understand that uptick, which is related to dark energy, that is the big mystery at the moment, trying to understand why the universe is behaving that particular way. If we think about it from the perspective of the light, let's just see, we've got a diagram here where distance from us is along the horizontal axis and time since the Big Bang is going vertical. So the bottom left, if you like, is the Big Bang. That's zero time, and we are 13.8 billion years after the Big Bang, and of course distance from us is zero. So there's us here and now in the top left hand corner, and there's the quasar when the light was emitted by the quasar. The quasar was about 5 billion years from us, and the light left the quasar 12 and a bit billion years ago, which means it was something like 1.5 billion years after the Big Bang. So that's where the quasar was in terms of distance from us at that particular time after the Big Bang. And when you ask what happened to the light from the quasar, well, you might say, well, surely the light is going to travel towards us, and of course the distance from us is going to get smaller and smaller and smaller as time goes by. So won't it do something like that? Won't the distance that the light has covered get closer and closer and closer to us as a function of time going by? Well, maybe, but not when you take into account the fact that space is expanding. We're back to the swimmer swimming against the tide, or an ant walking along a rubber band where the rubber band is being stretched faster than the ant can walk. The quasar is receding from us at twice the speed of light. So what actually happens to the light is, for the first few billion years, you can see here from 1.5 to about 4 billion years after the Big Bang, the distance that the light has made towards us, well, it hasn't. It's gone backwards. The light is further away from us a few billion years after it's left the quasar compared to the time where it left the quasar. The light is trying to work its way towards us, but space is dragging it backwards. So the light is actually increasing its distance from us, and it does that for a few billion years until eventually the light makes enough headway that it can actually start moving towards us. It takes over 2 billion years before the light can start to make enough headway such that the distance it has to cover gets smaller and smaller and smaller, and eventually it makes it to us 13.8 billion years after the Big Bang. If we think about what the quasar itself is doing, not the light, but the quasar, after the light has left 1.4 billion years after the Big Bang, when the quasar is 4 billion light years away, what happens to the quasar? Well, the quasar goes flying off into the distance. I've drawn it as a dotted line. It's heading off to something like 25 billion light years in the top right hand corner there. By the time you get to now, it's something like 25 billion light years away. I've drawn it as a dotted line because strictly speaking it isn't a straight line. Remember, I've shown you that the velocity starts high and then goes down a bit and then goes up a bit, so the velocity is changing, so it shouldn't be a straight line on a distance time diagram, because the gradient effectively gives you the speed at which the object is travelling. So it should be a slightly wavy line, but I couldn't work out exactly how to produce an accurate wavy line, so it's just a schematic reminding us that the light eventually works its way to us whilst the quasar goes flying off into the distance such that it's now 25 billion light years away. I call this ancient light because I reminded myself just how long the light has been travelling. And if you think about it from the perspective of the light was emitted by the quasar approximately 1.4 billion years after the Big Bang. It had already been travelling, the light had already been travelling for 8 billion years before even the Sun and the Earth were born. And it continued, of course, throughout the 4.5 billion years thereafter. Life evolved on Earth, the light kept on trucking. Dinosaurs came on, went, the light travelled on. In the last million years or so of its journey, it arrived at the edge of the Milky Way, crossed a few spiral arms, entered the solar system. In the last few hours of its journey, it arrived at Earth, travelled through the atmosphere in a fraction of a second, hurtled towards England, dodged a few clouds, entered the lens and hit the camera sensor. And it produced 1 pixel in the image. Just a pixel, but what a journey. So here's a graphical summary of what I've been talking about. There's the camera on the star tracker in the bottom left there, a Nikon camera with a 300mm lens, a large number of short exposures. I was pointing the camera where you can see in the top left inset, that orange rectangle tells you where I was pointing. The main image is the image I obtained with the star 80 Draco in the middle, and just next to that you can see in the top right hand inset a few stars, a few galaxies, and right in the centre, indicated by those 2 grey lines, are the quasar. So can you image a quasar using just a camera but without a telescope? Yes, it is possible to catch what I like to think of as the quasar's ancient light. Thank you all for listening.